Hi everyone, and thank you guys for being here. My name is Chiamaka, and today I'm going to talk to you about some of the work we've done concerning the role of cyclic phosphates in non-enzymatic ligation, and just studying some general principles of non-enzymatic ligation. So, not to belabor the point, but we all know that non-enzymatic nucleic acid replication is a complex process, and so there have been a lot of studies to try and understand this. And from our point of view, there are basically two ways in which people generally approach this. So in one case, you can look at polymerization of nucleotides. So you have a template, and you try and polymerize your different nucleotides on it. But on the second hand, if you can imagine that there was a template on the early Earth, then it's not too far to assume that there would also be short oligonucleotides. And so the questions we're trying to answer is how do you ligate the short oligonucleotides once you've hybridized them together? And so before we started this work, we looked into literature to see some of the things that people had been doing, because this problem dates back to decade-old problems. And so in general, like I said earlier, there would be a template, and the idea is you're trying to ligate what would be a short primer to your short strands. One of the features of your oligos, of your primer, is that it would have a phosphate, and you would need to activate this phosphate. So people have done this you can have an activated phosphate that you then include in studying your replication, but you can also include condensing agents, which can then activate your phosphate, and you can get your new strands. And some of the things we found about condensing agents in general was that even though this has been studied a lot in the past, there did not seem to be a consensus on which condensing agents were superior. So for instance, we looked at a lot of studies with cyanogen bromide, which has very fast ligation kinetics, but cyanogen bromide is highly toxic, and the fast ligation kinetics actually prevents you from understanding the mechanisms. On the other hand, we looked at water-soluble carbodiimides, and we found that it could take weeks and perhaps even months for you to get your maximum product, which again is a bit hard to tease out the mechanisms involved with ligation. And perhaps the most interesting thing that we found was that generally you had low yields for RNA ligation compared to DNA ligation. And this is interesting if you put it in the context of the RNA world. And also, and perhaps more interesting, is that a lot of these, so if you have an RNA oligonucleotide with a 3' phosphate, it would form a cyclic phosphate, which a lot of people believe to be an activated intermediate. And so if you have this activated intermediate for the RNA oligonucleotide, why don't you get higher yields compared to the DNA oligonucleotides? And so this brings us to the two questions we're trying to answer in this study. The first one is, what parameters affect the efficacy of chemical ligation? And the second one is how relevant or how does your 2' 3' cyclic phosphate actually enhance the rate of your chemical ligation? And to do this is our experimental design. So we have a hairpin, which we've optimized to be very stable, and we're going to try and ligate a short piece of oligo to the stem. Oligo is a 3' phosphate, and generally, we mix in our hairpin and our oligos together. After hybridization, we add in our EDC. So in this case, we're using EDC, a water-soluble carbodiimide, as a condensing agent. And after activation, we incubate it for a period of time at different temperatures, and we form our ligated products. And we typically run our reactions on a gel because our hairpin is fan-labeled, and so that allows us to see our products. And so this is just an example of, so in this study, we're looking at the effect of the activated nucleotide on ligation. So our hairpin is all DNA, and most of the short oligonucleotides, so most of the nucleotides on these oligos are DNA, except for the last one. So the last nucleotide is either DNA, RNA, or a 2' O-methyl. And the idea is that once we activate this with EDC, the EDC attaches itself to the phosphate, so creating a good leaving group for the ligation to continue. But in the case of the RNA, it forms a cyclic phosphate. And so, again, we're looking at the effect of this cyclic phosphate on enhancing ligation rates. And so in this first experiment, what we do is study at different temperatures. So this gel I'm showing you was taken after only 2 hours. So at different temperatures, what is the effect of having the different nucleotides on that terminal end? And so we see very quickly that for your DNA oligonucleotides, as you increase the temperature, you increase the rate of the chemical reaction. So this is kind of what we expected, but you can see that after only 2 hours, you're almost at 80% chemical ligation products formed at high temperatures. You see that for the RNA, though, even though we're forming a cyclic phosphate, and so we verified this with HPLC and LCMS, you don't get any products formed after 2 hours, whereas you get a lot of products formed for the DNA. But once you block that, the 2' hydroxyl with a methyl, so in our 2' O-methyl case, you see that as you increase the temperature, you get more products that are formed. It's also interesting to note that at low temperatures, so at 4 degrees Celsius, you don't see much of any products forming, and we think that this is because at this low temperatures, the 2' O-methyl it has a steric hindrance that is preventing this ligation from going on, and by heating up the temperature, you can reduce the effect of the conformation. And so we do this over a wide spread, so we do higher temperatures, but we also look at it for 2 hours and 24 hours. So the blocks represent 2 hours, and the dash represent 24 hours. And just generally, you see that at high temperatures, for the DNA and the 2' O-methyl, you get about the same rates of product, or the same amount of products that are formed immediately. But like I showed you earlier, and you might appreciate it more here, after 2 hours, the DNA is almost at 60% at 25 degrees Celsius, but the 2' O-methyl is only at 20%. And so what this showed us was that it's important to make sure your reaction has gone into completion. So if we had just looked at instantaneous rates, you might think that DNA ligation was perhaps better than 2' O-methyl. But that is very temperature and time dependent. We also saw that, again, even after 24 hours at 4 degrees Celsius, you don't get any products formed for the 2' O-methyl. But even under our best conditions, so 25 degrees after 24 hours, you barely see any RNA ligation going on. Now, we're not saying that you can get some products formed if you increase the amount of excess oligonucleotides that you have. So in this experiment, we had only 1.5 excess of oligos to the template, but if you increase it to, say, 20 times, if you saturate the amount of oligos that are present, then you can see some ligation happening. If you also increase the pH of the reaction, you can get some products formed. But in both those cases, the maximum product that you get is only about 20%. Whereas in our best conditions for DNA and 2' O-methyl, you get up to 80–90% product formation. And so having picked the best conformation, so we know we want to use a DNA oligonucleotide primer to do our ligation, we decided to look at the effect of sequences. So this has been done before, but in our case, we believed that we had optimized all the possible problems, and so we wanted to see if that would have any effect on our ligation reactions. And the thing to pay attention to here is that this dash, or this line, represents the nick of the ligation. And so in this first gel, again, this experiment was done after only 2 hours, but in this first gel, we're looking at the GG being opposite the ligation nick versus being at the ligation nick. And again, we look at it at different temperatures, and you see that when your GG, so when you have purines at opposite the ligation nick, you see a really fast increase in the amount of products that you get when you increase the temperature. But when you have the GG stacking at the nick of the ligation, then you see a decrease in the amount of products that are formed as you increase initially. So at 4 degrees Celsius, there's barely any product forming, but as you increase the temperature, then you can increase the reaction rate. And so again, like we saw in the case of the 2' O-methyl, there seems to be a difference, there seems to be some effect of stacking on our ligation rates. And so we do this, the same experiments at different times, so 2 hours and 24-hour studies, and we also scramble the positions of the G's and the C's. And you see that generally at high temperatures, there doesn't seem to be any effect on the sequences location. But after 24 hours, when you have your stacking at the nick of ligation, it really decreases the amount of products that you get compared to when you have your stacking opposite the ligation nick. And so we decided to look at whether this was just a feature of the GG base pairing system, or if this could also be applied if we had an AT base pairing system. So we kept almost everything the same, but now instead of CG closing base pairs, we looked at AT closing base pairs. And you see about the same effect that we observed. So in this first bar, when you have your purines, so your AA stacked opposite the ligation nick, you see a really fast increase in the instantaneous rate, and it approaches maximum. But when you have your purine stacking at the nick of ligation, then you see a decrease in the amount of products that are formed. And again, as you increase the temperature, you allow it to attain more conformation, and you can get more products that are formed. And so in conclusion, from just a general nucleic acid standpoint, we see that there are multiple factors that can affect non-enzymatic ligation. One of the first ones we looked at is just the effect of the sugar. So having a 2' hydroxyl versus an O-methyl on your oligonucleotides. We also saw that base flanking, so the position of the purines really affected how fast your reaction went, especially at low temperatures. And from just an RNA world perspective, we saw our data showed that the 2', 3' cyclic phosphate is perhaps not an activated intermediate in template-directed type ligation reactions. And with this, I'd like to thank NASA and NSF for funding the center, my group members, and my co-authors. And I'll take any questions.